We are often told that large language models are good at generating fluent text, but poor at actual reasoning. Early models like GPT-2 could write coherent essays, but failed miserably at solving logic puzzles or doing multi-step math. Why? Because fluency is not the same as understanding. These models learned patterns in data, not how to think. Over time, researchers noticed that simply feeding models more data and making them bigger hit a wall. Reasoning performance stopped improving. So, what changed? Scientists began introducing techniques that train models not just to repeat, but to reason, giving rise to a new generation of models that can actually show their work. One of the biggest breakthroughs was something called chain of thought prompting. Instead of asking a model to spit out an answer directly, you ask it to explain its steps along the way. This forces the model to think out loud, and it works. For example, if you ask it to add 237 and 468, it might now say 237 plus 400 is 637 plus 68 is 705. Much better than just guessing a number. But what if the model makes a mistake? And that's where self-verification comes in. Basically asking the model to double check itself before answering. This is like asking a student to review their math before turning in the test. It's more accurate, but takes more time. To make this more robust, researchers began using reinforcement learning. This means the model doesn't just learn from examples, it gets rewarded when it finds a correct solution. Models like DeepSeek R1 were trained this way, and they showed a big jump in reasoning skills. It's like teaching a dog tricks with treats. Do the right thing, get rewarded. But just like dog training, it can be slow and tricky. The reward signals must be chosen carefully, or the model learns the wrong thing. But there's a catch. Sometimes these smart models overthink. They keep generating more reasoning steps even after they've solved the problem. Why? Because they were trained to explain, and sometimes they don't know when to stop. Imagine a detective who solves a case, but keeps interrogating people just to be sure. This wastes time and makes the model less efficient. Understanding and reducing this behavior is a big challenge right now. Can we fix this just by giving the models more time to think? Unfortunately, no. Studies show that letting a model use more tokens, its internal thought space, helps up to a point, but eventually, even with unlimited space, the models fail hard problems. For example, on AIME 25 math problems, performance improves with more tokens, then plateaus, then drops. It's like giving a student unlimited time on a test. That helps on medium questions, but not on the hardest ones. They still need better strategies, not more time. So, how do we really know if models are reasoning well? Standard math data sets have a problem. They might be contaminated with similar examples from training. To fix this, researchers built puzzle environments like Towers of Hanoi or river crossing problems. These let you precisely control the difficulty and check each step the model takes. This gives a cleaner picture of what the model can actually do. For example, a model might do well with 2 disks in Towers of Hanoi, okay with 5, and fail with 10. This shows clear boundaries in its reasoning. Interestingly, across many tests, models show a 3-part pattern. On easy problems, even models that don't think do well. On medium problems, thoughtful models win. But on hard problems, both fail. It's like a race. Sprinters win the short run, marathoners win mid-distance, but nobody finishes an ultramarathon without training for it. This tells us reasoning must scale with problem difficulty, and right now, it doesn't. So where do things go wrong? If you look at the model's internal steps, its thoughts, you'll see a pattern. On simple tasks, the early steps are good, but then the model starts rambling and loses accuracy. On medium tasks, it starts messy but cleans up its logic near the end. On very hard tasks, it fails all the way through. This tells us where to intervene. For example, maybe we should stop the model early when it's about to start overthinking. In the end, even the best reasoning models still struggle with executing given algorithms. That's a sign they don't truly understand logical rules. They're faking it. Well, what's next? Probably hybrid models that mix neural networks with traditional logic tools. Models that not only write like humans, but also think like them. Right now, it's like giving a recipe to someone who doesn't know how to cook. They might follow the steps, but without understanding, they'll burn the dish. The evolution of reasoning and language models is a fascinating journey. It shows that intelligence is not just about words, it's about the steps behind them. We are teaching machines not just to talk, but to think. Large language models, LLMs, begin with impressive pattern recognition, but originally showed poor performance on formal reasoning benchmarks, highlighting a gap between language understanding and logical inference. Early models often failed to chain together intermediate steps or verify their outputs, leading to brittle or incorrect conclusions. Researchers found that simply scaling up data and model size improved fluency, but yielded diminishing returns on complex reasoning tasks. This motivated a shift toward specialized training phases and architectures, explicitly designed to enhance reasoning capabilities. Understanding this evolution is crucial for identifying both progress and persistent limitations in model intelligence. GPT-2 could generate coherent paragraphs, but consistently stumbled on multi-step arithmetic or logic puzzles. It's like teaching a student to read fluently without giving them the tools to solve algebra problems. They can pronounce the words, but not apply them to math. Chain of thought prompting asks models to articulate intermediate reasoning steps, improving accuracy on multi-step problems by making their thinking explicit. Self-verification further strengthens reliability by having the model review and correct its own chain before presenting a final answer. Both approaches leverage additional compute and carefully curated prompt data to coax better reasoning out of black box models. However, generating high-quality code examples is expensive, and the benefits plateau as reasoning complexity grows. These methods underscore the trade-off between transparency and computational cost in LLM reasoning. Asking a model to list each arithmetic step before summing yields correct results on multi-digit addition more often than a direct prompt. It's like having a student show their work on a test. Verifying each step reduces errors, but takes extra time and effort. Reinforcement learning, AL, with verifiable rewards, teaches models to prefer reasoning paths that lead to correct answers, rather than just imitating text patterns. By defining reward signals such as solution correctness or proof validation, models like DeepSeek R1 have matched closed-source baselines in reasoning benchmarks. RL enables models to discover novel inference strategies that supervised learning alone might not capture. Yet RL training is resource-intensive and sensitive to reward design, risking overfitting to specific benchmarks. Still, RL represents a promising avenue for instilling durable reasoning behaviors in LLMs. DeepSeek R1 trained with RL on math problems achieves similar pass rates to commercial models on Math 500. It's like using a reward system to train a dog to perform complex tricks. Effective, but requiring careful reinforcement and time. Large reasoning models, LRMs, sometimes produce verbose, redundant reasoning traces termed overthinking, even after arriving at the correct solution. This inefficiency inflates inference costs without improving answers, revealing a mismatch between solution discovery and explanation elaboration. Studies show models continue exploring alternative or incorrect steps after the point of solution, wasting computational resources. Understanding overthinking is key to making reasoning more efficient and focused. It also highlights that quality of reasoning is not solely tied to length or depth of thought. A model solving a simple logic puzzle may generate dozens of extraneous sentences beyond the necessary inference steps. It's like a detective who, after finding the culprit, continues to interview dozens of innocent witnesses just to be sure. Increasing inference token budgets allows models to explore longer chains of thought, improving accuracy on moderately complex tasks. However, beyond a certain complexity threshold, both thinking and non-thinking models collapse to zero accuracy, showing a fundamental limit to benefits from added compute. Moreover, some LRMs paradoxically reduce reasoning effort as tasks become harder, indicating poor scaling of reasoning strategies. These observations suggest that merely extending compute time cannot overcome inherent reasoning barriers. Future progress requires algorithmic innovations, not just larger budgets. On AIME 25 puzzles, granting more reasoning tokens initially boosts performance but eventually yields no improvement or even declines. It's like giving a student unlimited exam time. They improve on mid-level questions but still can't solve the hardest ones no matter how long they sit. Standard math datasets, Math Sheet 55, AIME 24/25, reveal general trends but confound reasoning with training data contamination and variable difficulty. Controllable puzzle environments like Tower of Hanoi or River Crossing allow precise tuning of complexity and validation of each reasoning step. These synthetic tasks isolate core reasoning abilities by removing dataset biases and ensuring systematic evaluation. Using puzzles, researchers can dissect model behavior across well-defined complexity regimes. This methodological shift provides clearer insights into when and why LLM reasoning fails. A model may perform similarly on low complexity math problems, but diverge drastically on puzzles with controlled move counts. It's like testing a car's performance on a closed racetrack with adjustable obstacles rather than random city streets. Across varied tasks, models exhibit three distinct regimes. At low complexity, non-thinking LLMs match or exceed thinking models. At medium complexity, thinking models hold an advantage. At high complexity, both collapse. This tripartite pattern reveals that reasoning methods only buy time up to a threshold, beyond which models lack fundamental problem-solving skills. Identifying these regimes helps calibrate expectations for model capabilities and guides targeted improvements, and also underscores that reasoning strategies must adapt dynamically to problem difficulty. In Towers of Hanoi, non-thinking models excel with 2 disks. Thinking models shine with 5 disks, and both fail beyond 10 disks. It's like runners. Sprinters win short races, middle-distance athletes excel in mid-range, and neither can finish an ultramarathon. Examining intermediate solutions within model thoughts reveals how accuracy and error patterns shift over the course of reasoning. In simple tasks, models often start correct, then deteriorate, overthinking. In moderate tasks, they improve accuracy later in their chain of thought. For very complex problems, correctness is near zero throughout, indicating collapse. Tracking solution positions and correctness provides a fine-grained view of reasoning dynamics. These trace analyses pinpoint where interventions such as early stopping or targeted guidance could most effectively boost performance. In a sliding tile puzzle, correct moves cluster early for simple sizes but only appear late for moderate sizes before vanishing entirely. It's like watching a chess player blunder early in a grandmaster game. They may recover temporarily but eventually lose as complexity increases. Current LRMs struggle with even the execution of provided algorithms, revealing gaps in logical step following and symbolic manipulation. They also display dataset biases, failing unexpectedly on puzzles rarely seen during training. Strengthening reasoning will require integrating explicit algorithmic modules or hybrid neurosymbolic approaches. Improving trace efficiency and mitigating overthinking are key engineering challenges. Ultimately, building truly generalizable reasoning models demands new architectures that blend learned patterns with structured, verifiable logic. Providing the step-by-step Tower of Hanoi algorithm in the prompt does not prevent performance collapse at high disk counts. It's like giving cooking instructions to a novice chef. They may follow early steps but still fail on complex techniques without deeper culinary understanding.